everyone, and welcome to today's Learn Live session. In today's session, we're going to be walking you through how to model data for Azure Cosmos DB for Postgres. My name is Gary. I work as a program manager on the Azure Cosmos DB and Postgres teams, and I'm super excited to be with you here today. I'm joined by Cédric. Cédric, do you want to introduce yourself?
Yeah, thank you, Gary. My name is Cédric, and I'm a solution architect at Capgemini Engineering and Microsoft Azure MVP, and I'm very happy to share this session with you.
Thank you, Cédric. So today's content is based on the model data for Azure Cosmos DB for Postgres learning module. This is the first module in the Azure Cosmos DB for Postgres series. In this module, we'll walk you through the core modeling concept step by step and show you some practical demos of its application. I encourage you to explore the entire learning path after our session today. This session is live, so please say hi, introduce yourself, and let us know where you're joining from. We've got a bunch of moderators in the chat. We've got Ivan, Josh, Vivek, and Lucas as our moderators for this session. They'll be able to answer questions as we go through for those questions that we aren't able to take live during the session. We'll try to save a little time at the end of the session as well for some additional chat. Let's see how it goes time-wise. So let's dive straight in. In today's session, we're going to help you identify the key considerations for modeling your distributed database using Azure Cosmos DB for Postgres. It will help you classify the various table types that are available to you and show you how to use them. We'll quickly show you how to create a cluster, how to create the schema and choose your distribution column, and how to evolve your schema as your workload changes over time. So let's dive straight into the content. Azure Cosmos DB provides a highly scalable distributed database solution by grouping multiple Postgres servers together as nodes in a cluster. Today, we're going to be playing the role of leads for Woodgrove Bank, and this will be helping their developers move their application from a traditional Postgres server to an Azure Cosmos DB for Postgres environment. They're skilled Postgres developers, but they have no experience working with distributed databases. Our job is to show them how to get the most out of the Azure Cosmos DB service. Cédric, will you introduce us to a little bit about the application?
Yeah, of course. So Woodgrove Bank is a company that develops a contactless payment application. So after a successful trial, the company would like to release the application across Europe and the United States. So as the application will need to scale, the data will need to scale as well. So Azure Cosmos DB for Postgres is built to host Postgres database and to support them at scale. In this module, you will help the developers move to a distributed data environment. First, we will start by looking at how Cosmos DB for Postgres processes a query at a high level and what it means to scale. After that, we will look at the three common table types in Azure Cosmos DB for Postgres, and we will see how those table types work with existing relationships in a Postgres database. To continue, we will talk about design consideration using the Woodgrove Bank already proven relational data model, and we'll see how to change it to fit in the distributed environment. So by the end of this module, we'll be able to determine which type of table to use and how to distribute the data effectively. So now it's time to prepare the application for growth. Woodgrove Bank is expanding, adding a corporate office and branches throughout Europe. Their contactless payment application is about to see growth in the number of users and locations. So with a substantial growth in users, the number of transactions will grow exponentially. That's why it makes sense to distribute the data across multiple servers rather than put all the data on a single server. Azure Cosmos DB for Postgres can help cases when coming from a standalone Postgres environment and needing to grow at scale. So as the Woodgrove Bank development teams need a quick proof of concept, they trialed their payment application with a single non-distributed Postgres database. Initially, they had only two tables, the payment user that stored the user using the application and the payment events table that store the events, the transaction generated by the user, such as, for example, give funds, send funds, and request funds. The following diagram illustrates the initial data schema. So the Woodgrove Bank team realized they need to normalize their data to store the data in a relational database. So they decide to migrate their event types and merchant to separated tables. The following diagram illustrates the normalized architecture. This normalized data diagram is what they use for their trial. However, as Woodgrove Bank is growing and needing a distributed environment, the developers suspect that this data diagram will evolve in the future. So before they can change their model, they need to understand what it means to distribute the data. So I will pass the turn to Gary that will explain how Azure Cosmos DB for Postgres operates for distribution.
Sure. So as I mentioned earlier, Azure Cosmos DB for Postgres operates as a cooperative group of individual Postgres servers, known as a cluster. The primary server to which clients connect is called the coordinator node. The coordinator manages the cluster and coordinates the distribution of data and queries to the worker nodes as they're needed. Before we jump into more details around the modeling of the data, let's have a quick look and understand what's involved in deploying a cluster. Here I have a resource group called LearnLife 2023. I'm going to quickly create Azure Cosmos DB for Postgres cluster. So, oops. Don't want to know about the new benefits filter. So we'll quickly look it up in the marketplace. Here's the service that we're after. We're going to click create and then have a look at a couple of the parameters involved in creating a server. So the first thing that we need to create to specify, besides the normal subscription and resource group, is the name of the server. I'm going to call it LearnLive now for the moment. We're going to specify the region, and most importantly, we're going to specify the configuration of the cluster. If I click on the configuration, I can select a single node, which is going to combine the worker and the coordinator node into a single instance, or I can specify a cluster that is going to be distributed across multiple nodes. In this case, I'll select two nodes. That'll give us two workers and one coordinator. I can specify the configuration of the compute nodes as well in terms of vCore and memory configuration, as well as the size of the storage associated with each node. So if I click save on that, I would need to specify a couple of other things. The version that we support, Cosmos DB for Postgres supports multiple versions. A password. The default username for admin user is always Citus in our case. There are other things that I would need to specify, but when getting it up and running for yourself, you would want to specify public access, which allows the cluster to be connected to the internet, and allow access from Azure services and resources to this cluster. I'm not going to create this cluster now, as we already have one. Let me show you what's involved in connecting to a cluster. So here's our cluster. This is a pre-created version of exactly the same cluster that I've just shown you how to create. You will see here the coordinator node name is specified once the cluster is created, and I'm going to connect to that coordinator node. So if I connect to that coordinator node, I'm going to do it using PSQL, and I'm going to go to the connection strings, pick up the PSQL command line, and it's provided here for me. I'm then going to open up a shell. I'm going to reconnect to my shell. It takes a few seconds to spin up the shell. And in the shell, I'm just going to specify the connection string as it appears here, with the host that I'm connecting to being the coordinator. So here, I'm just going to take out the password. I'm going to log in, and I'm now connected to my Postgres cluster as I would to a normal single node Postgres environment. Let's have a look and see what's involved in creating some tables. So I'm going to create some typical tables here. Oops, wrong copy. So let's create some tables here. Sorry, I'm having copy paste issues. Let's get that working. Sorry. I'm going to reopen the shell here, see if that resolves the issue. Otherwise, we're going to have very slow demos while you watch me type stuff. Give me 1 second. Let's see if that works. So here's our create table. There we go. So here we're creating the event types table as we would a typical table. Sorry, we are really having copy paste issues. Oh, sorry, I'm no longer connected either. Let me connect. Here. And then let's have a look and do our create table statement. Sorry, there seems to be something wrong with the shell today. We will get there. I'll give it one more try, and then we will fix that in the next demo. There appears to be something wrong here. Let me go back to the slides. We'll come back to the demo of connecting to the database. Cédric will pick it up in the next demo. Sorry. Let's go back here. So let me talk to you a little bit about how the data is distributed in a Postgres environment. This is a distributed SQL environment. We want to understand how to leverage all of the resources within that environment. All data is stored in a cluster. In the cluster is broken into shards. Each shard contains a subset of the data stored in any table. By default, Cosmos DB for Postgres creates 32 shards, and these shards are distributed across the nodes in the cluster. The distribution of rows to a shard and shards to the node is predictable and based on the values of a chosen distribution column. More accurately, it's based on the hash of the value of a chosen distribution column. This sounds complicated, but in reality, it's just as simple once you get an understanding of how things work. The coordinator contains metadata tables that track the row and shard placement. When a row of data or a query comes into the cluster, the coordinator looks up at the request and uses the metadata to identify the worker or workers that need that request forwarded to them. The worker nodes then process the request against the data stored on that node. And if it's a query, it'll return the results to the coordinator. The coordinator will then return the results to the client. By choosing the distribution column, well, you can ensure that the data and queries are evenly distributed across all nodes. You want all nodes to be involved in the distribution of the data. Each node should have an equal amount of data associated with your workload. For some large scan heavy queries, you'll want to engage all nodes to process your entire data set. For other queries and insert operations, you'll want to ensure that only the single node is targeted as part of that operation. For the remainder of today's conversation, we're going to be talking about distributing data and queries across nodes. We're going to leave out this detail around the shards themselves, that intermediate layer. Woodgrove Bank have been experimenting and initially decided to distribute the events based on merchants. Merchant ID seemed like a good choice for a distribution column. In this example, you can see the payments event table distributed across the shards on multiple nodes based on the merchant ID column. Here you can see the merchant ID column on each of the nodes contains unique values. Each node contains a non-overlapping subset of the data. All data associated with a specific merchant ID is stored on a specific node. Let's have a look at inserting data. Here we are inserting a row with the merchant ID ending in 596. The client will submit this to the coordinator node. The coordinator node will calculate the hash of the distribution column value, look up the node associated with that value, and then forward the insert to that node for insertion into the appropriate shard. So all rows with the same distribution column values end up on the same node. That's the important thing to remember. Here, we're now looking at a query, and let's have a look at the query for all rows for a single merchant. A query with a where clause that filters on the merchant ID with a value ending in 596. The coordinator would receive the query, assess the filter clause by looking up the hash of the filter values. It would forward it only to those nodes that are needed, in this case, worker node 1. Worker node 1 would execute the query, return the results to the coordinator, which would in turn return the results to the client. Only a single node was required to process the data for this single merchant, as this was the only node where that data was stored. If we have a look at a more complicated query, let's have a look at an aggregate query where we want to count all the merchant transactions for a merchant by merchants, kind of a complete list. In this case, the query would be received by the coordinator. It would assess the query needs and send it to all worker nodes. Each worker would calculate its subset of the merchant's data and return the result to the coordinator, which would then combine the result and return the results to the client. With that, let's dive into the options for choosing specific table types.
So there are 3 types of table that can be created in Azure Cosmos DB for Postgres: local tables, reference tables, and distributed tables. You must retain that all tables on Azure Cosmos DB for Postgres start on the coordinator node as local tables and are created using the regular Postgres create table syntax. After that, a local table can be converted to reference table or distributed table. So local tables are tables of data that may be related to the application that consumes the data in the database. As we said just before, local tables live only on the coordinator node. An example of a local table could be a user authentication table. Next, reference tables are smaller tables of data replicated across each of the worker nodes that are frequently linked to the distributed tables. As the reference tables lives in duplicate on each worker node can access the data of reference tables without needing to access extra records from another worker node. For example, in the contactless payment application, the event types table contains only 11 records of the type of the events. So it is a smaller table and a good candidate to be a reference table. A reference table is created by the create reference table function. So for example, this query will convert the event types table from a local table to a reference table. Finally, reference table can be joined with local tables. They can also be joined with distributed tables. Next, distributed tables are large tables of data that are broken up into smaller chunks known as shards. The tables are sharded or distributed by a column known as the distribution column. Example of distributed table for the Woodgrove Bank application are the payment users and the payment events tables. Distributed tables can be joined with reference tables. However, distributed table cannot be joined with local tables. And we will use the create distributed table function to convert a local table to a distributed table. So to summarize, there are 3 different types of tables that are stored differently across the nodes. A local table is stored on the coordinator node, and that is very important. A reference table is stored in a shard on each worker node with all of this data duplicated and kept in synchronization across each of the nodes. And finally, a distributed table is shared over the worker nodes.
Sorry, here you can see the various table types depicted graphically. The metadata tables are shown in this light blue. The local tables are shown in green. The distributed tables are shown in blue, and the reference tables are shown in red. We'll keep this annotation going throughout the presentation today.
So it may be unclear whether a table should be a reference table or a distributed table. So to solve the challenge, we have to keep in mind the following question. So for example, how much data is on this table and how much growth is anticipated? How often is the data used in queries with distributed tables? What are also the performance implications if this data were duplicated across worker nodes? And finally, does the data need to be duplicated or shared? So to answer to this question, we have to take into account these considerations. If the data is joined with distributed tables and is a smaller amount of data that can be duplicated across worker nodes, and then the data, could be a good candidate for reference table. Now, at the other side, at the other end, if the data is a larger amount of data where duplication of the data could impact performance, then the data may be a better candidate as a distributed table. So for example, for Woodgrove Bank, should the payment merchant table be a reference table or a distributed table? So to answer to this question, we know that merchant will grow, but not at the rate of users or events. We know also that the merchant list will be relatively small compared to user and events. We know finally that the merchant list isn't anticipated to grow at a rate where duplication would impact performance. So the payment merchant tables make sense to be a reference table. So finally, for the Woodgrove Bank tables, we have the following design. Payment merchants is a reference table. Event types is a reference table. Payment events is a distributed table. And payment users is a distributed table.
So understanding distributed query processing at a high level is not sufficient to ensure efficient query processing for a specific workload. You need to understand your query workload and the data that is supporting that in the underlying tables and how they relate. For Woodgrove Bank, we need to consider this for all of their tables, events, event types, merchants, and user data in their applications. Let's touch briefly on primary keys. Primary key constraints on a table in a traditional environment may no longer make sense as a primary key in a distributed environment. For a primary key to be enforced in a distributed environment, the key must contain the distribution column, or we can drop them completely and ensure uniqueness elsewhere in the application. Now let's consider the important job of choosing a distribution column. When choosing a distribution column, you want to consider that the column should be a core part of your application usage pattern. The column value should be highly varied with a high cardinality such that they will statistically balance the distribution of data across your nodes. I mentioned that earlier. We want all nodes to participate in our queries and therefore need to ensure that all nodes have some part of our data. The column should also appear in the most common queries to allow parallel or efficient independent execution of the majority of the queries in your workload. Lastly, you want to ensure that tables that are queried together are co-located. Co-located means that all data needed is stored on the same node and that the tables involved share the same distribution column, thus allowing the node to fully resolve the query when it's executed. At Woodgrove Bank, the team investigated further and discovered that user ID makes sense as the distribution column because it's central to the application and appears in most queries. Distributed tables are created with the distribute table function, which takes at least two parameters, the name of the table to distribute and its distribution column. Here you can see the query that will distribute the users table from its local version into a distributed version using the user ID. The choice of distribution column on the payments events table is less clear. The merchant ID column might be a good candidate, especially if the merchant's table was distributed, and the merchant's details and events could be co-located by the same merchant ID column. In this case, the deciding factor on the distribution column will be understanding how the data is queried and identifying which scenarios could benefit more from co-location of data. Looking at the payment users table and the payment events table, distributed on user ID and merchant ID respectively, it is immediately evident that any queries on the user ID table would need to involve multiple nodes, as any specific user ID could be distributed across any of the nodes in the cluster, in the events table at least. You can see user ID 1894 resides on multiple nodes in this example when you distribute in this way. Given that the stated heavy usage pattern involves user ID, if instead we distribute it on the user ID, we transform the local table into a distributed table where user IDs of the same value reside on the same nodes. And now the user ID tables and events table are co-located. Queries that join the users and events tables can be fully resolved on each node for their subset of data, and the results return to the coordinator for return to the client. There is some challenges, though, that we still need to overcome. Cosmos DB does implicit co-location. Implicit co-location means that unless you specify the co-location details when distributing the table, the system will automatically co-locate the table. It does this by default using distribution column data types, placing the tables with the same distribution column data type in the same co-location group. By querying the Citus tables metadata table, you can see the distribution columns and co-location of each table in this visual presentation. Here, you can see that the payments events and payments users distributed on user ID have the same co-location ID. That makes sense. We want to be able to query across that. However, payment merchants is distributed on merchant ID and also resides in the same co-location group. This does not make sense as the values of the distribution column are not the same. We could have overwritten this in the create stage with the co-locate with parameter set to none. This tells the system to explicitly not co-locate the table with other distributed tables. Foreign key constraints in a standalone application make sense. However, in the distributed environment, foreign key constraints are tricky. This is because in order for a foreign key constraint to be enforced, the referencing and reference rows need to be stored in the same node. Here are some examples of the tables that are supported and work well together. Between two local tables are stored on the coordinator node, and because they're stored locally, they can resolve foreign key constraints. Between two reference tables, because reference tables are replicated to all nodes, data is available on all nodes to resolve those foreign key constraints. Between reference tables and local tables, because reference tables are replicated everywhere, including the coordinator node, you can reference between reference tables and local tables. Between two located distributed tables with the same shared key is the typical use case for distributed tables that are co-located, and it's the one that we're going to try and optimize our workload for. From a distributed table to a reference table, this is scenarios where the reference table is replicated on all nodes, and the distributed table, whilst it may have a subset of values in it, it has available to it the reference values that it needs to enforce the foreign key constraint. The case for foreign key constraints aren't supported is from reference tables to distributed tables. You need to bear that in mind in your design as you go through each of your table evaluations. Foreign keys that are involved in sharded data must include the distribution column. So where we talk about shared distribution key between co-located distributed tables, it's important that they have the shared distribution column. The distribution column must also be included in primary keys and unique constraints. This requirement means that going from a standalone relational environment to a distributed relational system may require updating your constraints from simple keys to composite keys that include the distribution column. For Whitgrove Bank, here are some changes that we'll need to make. In order to keep the foreign keys on the events table to the users table, the user ID needs to be the distribution column for both tables, so they have that shared distribution column. The foreign key relationship between events and events types works because it's going from a distributed table to a reference table. Keep in mind that reference tables don't have a distribution column. They're replicated to all nodes. If the merchants table is distributed and the user ID isn't part of the merchants table, the foreign key relationship between events and merchants would need to be removed. It'll no longer be enforceable. However, the developers at Whitgrove Bank realized that the merchant table is small and decided to make it a reference table as well. With that, the foreign key relationship can then stay, and the result is a relationship between a distributed table and a reference table. The events table is a distributed table, and the merchants table now becomes a reference table. With that, let's go back for a demo. I hope this one works better than the last one.
Okay, so now I will share my screen. So you can see my my Azure portal. It's okay?
We can see.
Okay, so I created the local tables described previously by Gary. So the event types table, payment users, payment merchants, and payment events. So now I'm connected to my Azure Cosmos DB for Postgres database instance. So here we can see the 4 local tables. And if we inspect the Citus table, we can see there are no reference table or no distributed tables. So now I will start the demonstration by create a reference table by running this query. So this query will convert the event types local tables to reference table. Why? Because we know that event types is a smaller tables, and we need to join the event types table with the payments events table. So it cannot be a local table, and it should be a reference table. Same remark for the payment merchant table. With this query, I will convert the local table into a new reference table. And now we will speak about distributed tables. So first, I will distribute the events by running this query. And I distribute the events based on the user ID column. Now I do the same. I convert the payment users local tables to a distributed table, and I will distribute the data based on the user ID column. Now, once again, I will inspect current design state by requesting the Citrus table. And now you can see some reference tables and some distributed tables. You can see also that the payments events and the payments user table are implicitly collocated because of the data types of the user ID column. So great, it works. So now I will stop the sharing. That's okay. So go back to the slide.
Are you seeing the slide?
Yeah. So to summarize, we have seen how to create local tables, reference tables, distributed tables, and we have seen also how to inspect the current design state by requesting the Citrus tables. So now it's time to talk about partition time series data. So when dates and times are involved, data may be kept or pruned for certain periods. Data may be also be queried frequently over a predefined time interval. So time partitioning can assist with these features. Woodgrove Bank can take advantage of time partitioning for showing data within a period of time and archiving or removing no longer needing data. Time partitioning is a feature of Postgres, allowing a table to be split by time ranges into virtual indexed table known as partitions. So when a table is created, the time partition is indicated by a partition by range clause with the name of the column that serves as the partition key. The partition need to be created in order for the system to use them. Individual partitions can also be dropped if the data is no longer needed. Time partitions can be managed using the create time partitions and drop all time partition functions. For Woodgrove Bank, the payment events table is partitioned by the created file as it's created as file, as it is shown in the following query. There is a couple benefits to using time partition. The queries will row only over the partition that are needed rather than over the entire dataset. By breaking the data by time range, it's easier to archive or delete the stored data. Woodgrove Bank only shows 6 months of transaction within their contactless payment application. After 6 months, those transactions are deleted for the context of this application. By using time partitioning, it's easier to query only the data to show and identify which data to prune and where it's no longer needed. Users of the Woodgrove Bank also have shown that they query data within a couple weeks. With this revelation, it makes sense to partition the data in intervals of 7 days. While the partition K is specified by the partition by range clause, this clause only indicates that partition will be used. The partition needs to be created and dropped outside the table creation process. The create time partitions function is used to create the time series partition with the following parameter. The table name that specifies which table to partition, the partition interval, which specifies an interval of time for this partition, the start from parameter that is optional and it specifies when to start partitioning. The default value is now. And finally, the end date parameter that specifies when to stop partitioning. For Woodgrove Bank, once the payment events tables is created and has the created at colon flagged as its partition colon, then we can run the following code to partition the data in 7 days increments. To expire the partition, call drop all time partitions with two parameters, the table name and the expiration period. To expire, Woodgrove Bank application data older than 6 months use the following code. That is not shown here. So it is call drop all time partitions and first parameter payments events and now minus interval 6 months.
I'll quickly demo it shortly as well.
Yeah, as partition creation and dropping all partition happen only when called, I suggest you schedule this maintenance to run automatically. In Azure Cosmos DB for Postgres, partition can be created on local reference and distributed tables. The partitions can be created prior to distribute the table or after distributing the tables. Partitions are different from shards in that partitions are vertical slicing, whereas shards are horizontal scaling. The partition details are managed at the worker node level, whereas the coordinator node is responsible for the distribution and shared placement. The partition column doesn't need to match the distribution column. So let's look at how these partitions are implemented in Woodgrove Bank payments events table. This diagram shows how the payment events table is horizontally scaled by the user ID. The transaction for user are stored together on a single node. For example, for the user number 1894 payments events live on a worker. For the user number 2000 payments events lives on another worker. And other events for the user number 2000 will be stored on the same worker node where the existing events are already stored. This diagram also shows how the shards are partitioned by the created at colon.
So let's have a look at that in a demo quickly. Here is the table that we've just had a look at. The payments event table, you can see it's partitioned, but there are no partitions created as yet. If we create the time partitions using the create time partition function, like this, we're specifying that we want to create a set of partitions for each week, for the previous month, and for 3 months ahead of where we are now. This will allow us to have a set of tables or have a set of partitions that we can load data into, one for each week, and manage them one by one. In the scenario that Cédric spoke about, we spoke about the drop old partitions table. So if we have a look at the partitions that exist today, you will see that we have a large number of partitions. You can see the date range goes back to 417 to 424, and the most forward-looking one is 0828. And there's a number of partitions here for each of the weeks between those two times. If we have a look at the drop old time partitions function, it allows us to specify what range of partitions we wish to drop on what table. In this case, we provide the partitions, the payment events table, and we specify up until when we wish to drop those. So because we specified now, those partitions that were previously created for the month, the historical month, are now dropped with a single operation. If we have a look now at the payment events table, again, you can see that those partitions now no longer exist. The first partition starts on 05/2022 rather than the previous one. Let's go back to the slides. And with that, we want to talk about how you evolve this. We've spoken about how you create it all up front, but you need to think about how you evolve this with time. What if Woodgrove Bank created their initial distributed database by starting with their original database design, i.e. not a distributed database design? Suppose they created that database as is on Azure Cosmos DB for Postgres. In a non-distributed environment, these relationships would work. In Azure Cosmos DB for Postgres, they will also work, but they will only work on that coordinator node. If the users applied the DDL that they typically applied, that would work on that distributed node itself. If the developers loaded data into that environment, all of that data would have been loaded onto the coordinator node. What we want to demonstrate to you is if we start with that schema and walk through the process that we've just walked through in our design, but in a physical way, you'll be able to get an understanding of all the commands required to transform your data step by step as we move through that process. So let's do that in a demo-driven way.
So let's start for the last demonstration. For this demonstration, I drop the tables created during the previous exercise, and I recreate the 4 local tables for events, user, and so on. So we can see here these tables, these local tables. And if we inspect the Citus table with the select query, with this select query, you can see that there are no reference table or no distributed tables. So first, after that, I will adjust the dependency and I will drop the foreign keys in order to get the relational database ready for distribution. So I will run the 2 following queries, right? And now I will create a reference tables for the event types. Remember, it is a smaller table, so it is a good candidate to be a reference table and should be linked with the payment events. And I will create 2 distributed tables. I will distribute the users based on the user ID column, and I will distribute the payment merchants based on the merchant ID column. Now, if I check the current design state, now we can see the reference table and our 2 distributed tables. We can see that the merchants and the users are implicitly collocated because of the data types or their distribution column. So the development teams realize that the merchant ID and the user ID columns do not represent the same entities. So, for example, the merchants should not be collocated with the user. So now I will update the collocation settings by running the following query. This query uses the update distributed table collocation function, and I will pass the collocated with parameter with the value at none. So I will run the query, and after that, if I check the design state, now we can see that the merchants and the user are not collocated. That's great. To continue, I will create a distributed table for the payment events, and I choose the merchant ID as the distribution column. Okay, down. If I check the design state, now I can see that the users and the merchants are collocated implicitly, but the developers are thinking and are starting to see that the file don't match, and it doesn't seem like a good distribution column. So because they want to join the payment events in the payment user table on the user ID. So I will update the payment events table, and instead of using the merchant ID distribution column, we will use the user ID distribution column. So I will run this query that uses the alter distribute tables, and I will pass the distribution column equal to the user ID. And now, if I check the state, we can see that the payments events and the payment users share the same distribution column, the user ID, and they are, of course, implicitly collocated. So now I will pass the turn to Gary that will adding foreign keys to a distributed table after creation.
So if we have a look at the table here, this should be in the same state that Cédric left off. We see that we don't have any foreign key constraints enforced, and we want to enforce a constraint from payments events to our payment users. That would look something like this. And if we run this, that works successfully. So that's going from our payment events table, which is distributed on user ID, to our payment users, which is also distributed on user ID. If we have a look now at the payment events table, we can see that it has that constraint now enforced. If we wanted to do the same thing for our merchants table, when we attempt to do this, you will see that the foreign key constraint fails. And that is because our merchants table is distributed, but it's distributed on merchant ID. So I would need to undistribute my merchants table. And the way that I do that is through the undistribute table function. That will convert the distributed table back into a local table. But that's still not what I want. I want it in a format that is accessible across all nodes. So I will then convert that to a reference table using the create reference table syntax we previously used. At which point I'm now able to, through the same query I ran earlier, by altering the table, I'm now able to add that constraint. And if we have a look at that table again, we can now see that it has that wrong one. Sorry. It now has that constraint applied. Sorry. So here we can see both of our constraints are now enforced. Let's switch back to the slides and have a look at a couple of questions as follow-up, a quick knowledge check on you guys. So let's jump straight in. We've only got a very limited amount of time. There's a distributed table to track events. Suppose the app users want to categorize the events and provide a small list of categories associated with that. What type of table would be used for these categories? So if you think about that, we have a small amount of categories. We want to link this to the events table. So think about how the events would be structured, and then think about how we would then structure those categories. It's also a small table, so we're not talking about a lot of rows. So the right answer is that we would want it to be a reference table. We would want that table to be distributed across all nodes in our cluster. Let's have another go. Which of these scenarios is incompatible with foreign keys in Azure Cosmos DB for Postgres? Between between a reference table and a local table? Between B, a reference table and a distributed table? Or C, between a distributed table and a reference table? Which of those would not work? The key to this question is you need to think about where the data resides in order for that foreign key to be enforced. The answer to that is from reference tables to distributed tables. Reference tables are available on all nodes, but the distributed tables that you would be wanting to draw a foreign key constraint on only have part of the data on any one of the nodes that you would have that table on. So it would be hard to enforce.
Now, the Woodgrove-bound developers added the payment categories tables. Which command will show the table and its distribution details? So remember, during the demonstration, we used this query, this command, several times. So according to you, what is the correct answer? So you run a select from the Citus table, you run a DT command or \d payment categories command.
So the table is a metadata table that allows us to see the configuration, and we've probably showed it 20 times if we showed it once in our demo today. With that, that brings us to the end of the session. Thanks for joining us. Apologies for some of the tricky start in the beginning with the demos. But in summary, what you've allowed us to do is show you the key considerations that you have when modeling data for Azure Cosmos DB for Postgres. We've showed you the different types of tables and how to choose the correct type of table for your workload, how to create a cluster and how to create the tables physically on those clusters, and then how to transform your schema as your application evolves. That should give you a comprehensive understanding of the basic operations required for modeling data for a workload that is changing. With that, we literally are right up against time. So thank you very much for your time. There's a bunch of resources available. So please click through on the link or scan the QR code. I'm hoping that all the questions have been answered in the chat. Many thanks.
Thanks, everyone.
Thanks, Cédric. Cheers.
Thanks, Gary.